Greetings, Mr. Eicher here. We're going to look at an investigative task, the AP Statistics exam. Typically the very last FRQ, question number 6, is an investigative task. On the digital exam this year, 2021, the 4th question is the last question, and that's an investigative task. So this question we're going to look at is from 2011. Let's take a look. If you haven't had the opportunity yet to read the question, go ahead and pause the video and read this question. And I'd encourage you to underline important terms and words, which I will do. We have a random sample of 9,600 students, 12th grade students from the US. Took maybe an 8-push exam. 9,600 students, 28%. That's a really important value right there. Both of those, the sample size n and the p-hat of 28%. And 28% of 9,600 is 2688. Another really important term here, you said let p be the proportion of all students who would answer correctly. Construct and interpret a 99% confidence interval for p. So in this investigative task, in part A, we're asked to construct and interpret an interval. We've done that many times. I would encourage you to remember to check conditions to make sure the interval is appropriate. We're going to use a 1 proportion z interval known as 1 prop z int on a TI graphing calculator. We'll use that if the conditions are met. We have RIN. We only have one sample, so we don't need the G in ring, just RIN. R for random sample of 9,600, this condition is met. Since we have a random sample, we can generalize to all 12th grade students. That's what we want to estimate, the proportion of all students, and we can do that since we have a random sample. I, the independent condition. Since we're sampling without replacement, we really don't have independence, but we can ignore that as long as the population is huge, that is bigger than 10 times the sample size. So 9,600 times 10 is 96,000 12th graders in the US. You could say we assume that's the case, but I'm pretty confident there's more than 96,000 12th graders in the USA. And then lastly, for the normal condition, with a confidence interval, we check the number of successes, which is n times p-hat, should be greater than or equal to 10. And the number of failures, n times 1 minus p-hat, needs to be greater than or equal to 10. Up here, I calculated p-hat times n and got 2688. So we have 9,600 times 0.28, that equals 2688. That's bigger than 10, that's good. And then the other one, 9,600 times 1 minus 0.28 is 6912, and that's also obviously greater than or equal to 10. What this tells us is the sampling distribution of p-hat is approximately normal. This part right here isn't required on the AP exam, but it's good to review. How do we determine if a sampling distribution is approximately normal? We use these. If we have intervals, we use p-hat instead of the true parameter p. This word here is essential. If you don't say approximately normal there, you would not get full credit on the AP exam. So we've checked conditions. Now let's construct our interval. We'll review 2 ways to do that. So to construct our interval, we have our statistic, which is p-hat, plus or minus z star, times the standard error of the statistic, which is p-hat, 1 minus p-hat over n. Plug in the numbers in, we get this interval. Just to remind you, the value here for z star, the critical value, on my calculator I used inverse norm. It's a 99% interval, so I have to add the tail on the left when I input that area. And then the mean and standard deviation is 0 and 1 respectively, and I got 2.576. That's one approach. If you're comfortable with that formula, then go ahead and write the formula. That's definitely better communication than writing something like 1 prop z test, but if you did it that way, 1 prop z int, you're asked for x n and the confidence level. So x I got by doing 0.28 times 9600, and that gave me 2688. And I put all that stuff in my calculator, and I get this interval, I'll round it to the nearest thousandth. These answers this should also equal that. You can double check that if you like. Lastly, we need to remember to interpret the interval. We've checked conditions, we have calculated the interval. We would say we are 99% confident that the interval captures and then whatever the parameter is in context. To get full credit on the interpretation, you need to mention specifically your 99% in there, 99% confident. You need to refer to the interval, which we did right there. And the interval is capturing a population parameter. You could use the word population, but I've used the word unknown proportion. That's my parameter I'm seeking to estimate. And the population is all US 12th graders. It's important also to use present or future tense, so who would answer this question correctly. If you said something like who answered this question correctly, that's confusing now because it sounds like you're talking about the sample proportion. We're talking about the sample. We want to talk about the population, or the population parameter, not the sample. This part was scored with 2 E's. So if you're able to check conditions, calculate the interval, and interpret the interval correctly, then you're already at 2 out of 4 points. That seems pretty generous in some ways, but I'm very thankful that that was the case because we really haven't done anything investigative yet, and you've already got 2 out of 4 points. So let's read on. This next section, assume that students who actually know the correct answer have a 100% chance of answering the question correctly. And students who don't know the correct answer guess completely at random among the 4 options. What this is doing for us is if a student knows the answer, they will get it right. They won't have an accidental, they bubbled in the wrong answer option. Like if they know it, they will get it right. If they don't know it, then they're not narrowing down. I know this isn't like entirely realistic. Students can usually throw out 1 or 2 options. But the assumption that the exam writer wants us to make is, hey, if they don't know it, then they're guessing completely at random from all the 4 options. So we will let K represent the proportion of all 12th graders who actually know the correct answer. Note that this interval we had is the proportion of students who would answer it correctly. Some of these people in here may have guessed and gotten it right. We would like to know who actually know the correct answer. So that leads us to this part B, which is an investigative part now that we're starting. We've used tree diagrams before, but never in this context. And this is a great example of an investigative task, using something that you know in a new context. This says in part B, a tree diagram of the possible outcomes for a randomly selected 12th grade student is provided below. Write the correct probability in each of the 5 empty boxes. Some of the probabilities may be expressions in terms of K. So we have a tree diagram, outcomes for a randomly selected student. Let's get this whole tree diagram here. Okay, so with tree diagrams, if you made your own tree diagram, you'd start on the left and kind of work your way over. So we have this branch is there's a probability of K that they know the correct answer. That would mean this probability is they don't know the correct answer, they're just guessing at random. Well, with tree diagrams, this branch plus this branch should add up to 1. So our probability here should be 1 minus K. So for instance, if the probability of someone knowing the question is 70%, then this obviously would be 30%, 1 minus 70%. And let's look on at the top here. If they know the correct answer, we were told on the previous page that they will get it right if they know the answer. They're not going to mistakenly bubble the wrong answer option or something. And there's a 0% chance that they would get it wrong because they know the correct answer. Multiplying across the branches, we get a probability of K. Multiplying here, we get a probability of 0. And we just need to fill in the bottom 4 boxes. So if the student is guessing, guessing at random out of 4 options. The probability that they would get it right would be 1 in 4. There's only one right answer. They're guessing out of 4 options, so 1 in 4. Probability they get it incorrect would be 3 out of 4. So now we can multiply across these branches, and we get an expression like they warned us in the directions. We would get 1/4, 1 minus k, and this one would be 3/4, 1 minus k. You could also use decimals, maybe distribute. You could write it as 0.25 minus 0.25k. You could write it like that. You could write this one as 0.75 minus 0.75k. There's different ways of getting equivalent expressions, but there's the tree diagram. So this is a little investigative. We've never been provided a tree diagram like this. We've never really had an expression that we multiply across the branches, but nothing too crazy, but it is new, it is different, it's investigating something. So on part C it says, based on the completed tree diagram, express the probability in terms of k that a randomly selected student would correctly answer the question. So we're looking for the correctly answering the question. That would be these people correctly answer and these people correctly answer. So as you may remember, if you add all these probabilities on a tree diagram, you would get 100%. Those are all the possible outcomes. So when you add them, you get everybody 100%. But we want this probability. Those are people who actually know and got it right. And we want this probability. We could also use this one. That's the people who guessed and happened to get it right. So in terms of k, we would have k plus 0.25 minus 0.25k. This would be an expression representing the proportion of 12th grade students who correctly answered the question, whether they guessed, like these people who guessed, or whether they actually knew the answer. We can simplify this a little bit. It looks like 0.25 minus 0.75k. That's just adding like terms. You can add this k with this minus 0.25k. So part B and part C were scored together if you had the tree diagram correctly filled out and you had the expression, and there were numerous ways that you could write the expression. You could even leave it like that kind of thing, as long as you have some expression in terms of k. That would be scored as an E for part B and C. On the last part, the investigative part, is question D, and that was scored as an E all by itself. Using the interval from part A. Now pause right there. We really need to use our interval in part A. They're serious about that. So let's go back to part A. My interval was that one right there. So 268, 292. Let's write that down. 268, 268, 292. Okay, I got my interval from A. And your answer in part C. Oh, my answer in part C is this guy. And interpret a 99% confidence interval for K, the proportion who actually know the answer. You may assume conditions are met. Thank you. So this is a great example. On investigative tasks, you will often be asked to use your previous answers. So I've listed them so I remember to use them. Now, this endpoint is the percent who got it correct. This expression represents the percent who got it correct. So if I take the endpoint and set it equal to this expression, I would be able to solve for K. And if I did that for both endpoints, then I can solve for K and have a new interval. Basically, I'm transforming the endpoints of my first interval into a new interval to be in terms of K. As I calculated that, I was getting negative answers, and then I realized, I'm going to go back and make this a plus because I had a 1 minus 0.25, and I accidentally wrote a minus there, but it should be a plus. So thankfully, them asking on part D now helps me get part C fully correct. Solving for K in both of these, I get 2 values for K. All I need to do now is interpret the interval in context. We are 99% confident, just like we were before, that this interval is much lower than the original interval. The first interval was the people who actually answered correctly. This interval, maybe a little surprisingly, is the interval showing the percent of students who actually know the answer, didn't just guess and got it right. Captures the unknown proportion of all US 12th graders who actually know the answer to the history question. So if you were able to use an expression and solve for the values of K and then interpret correctly, that would be scored as an E. And if you had all 4 E's, then you would get a 4 out of 4 on investigative tasks. Those are really, really uncommon to get a perfect score on the investigative task. I'd encourage you to try to get 1 or 2 points, at least from the first part. Part A is typically something that has been done directly in class. So it's basically getting the low-hanging fruit, as they say. Get the points, get the easiest points that you can get. Well, I hope this video looking at AP Stats FRQ 2011 number 6 was helpful for you. Hope you had some big picture good tips of what to do when facing the investigative task on the AP Stats exam. Good luck on the exam. See you next time.